The laws of nature can provide some powerful effects, and electrostatics is no exception. Sometimes those effects are not as dramatic, but still provide an excellent way to annoy your little brother. But our job is to explain why they happen. It's time to talk about static electricity. Welcome to Flip Physics. Today I'm going to talk about electrostatics. There are four fundamental forces of nature: gravity, the weak nuclear force, the strong nuclear force, and the electromagnetic force. Every force in the world, when taken down to a basic level, is one of those four forces, or some combination of those forces. In previous videos we've talked about gravity, but now it's time to move on to electromagnetism. The electromagnetic force, although really one big force, is often broken down into magnetic forces and electric forces. I'll talk about magnetic forces in a later video. Today let's focus on electric forces. So, what is electrostatics? Electro means electricity, statics means not moving. Although electricity is a continuous flow of charge around a circuit, electrostatics deals with charges that are built up in one location, charges that are not continuously moving. When charges are stationary, they produce electric forces. As we'll find out later, when they move, they produce magnetic forces. Benjamin Franklin is a well-known figure for a lot of things, but one of the things he's known for is his study of electrostatics. He realized there were two types of charge, an A charge and a B charge. He realized that when you move the two types together, they attract, and if you move two A charges together, they repel. Or if you move two B charges together, they also repel. He realized that opposite charges attract and like charges repel. He had no idea what those two types of charge, A and B, actually were. He simply realized they existed and made some observations about them. He realized that some things produce a charge of type A and some things produce a charge of type B. Only later did we figure out what the A and B charges actually were. We called them positive and negative charges, but those are really just names. They're completely arbitrary. We could have called them black and red charges, or we could have called them 0 and 1 charges. It really doesn't matter, there are just two types. As we discovered later, everything in the universe is made of atoms, and those atoms contain positive protons in the nucleus, and they contain negative electrons orbiting around the outside. In the case of most electrostatic situations we're looking at, these are the main sources of positive and negative charge. Negative charges, electrons, are free to move, whereas positive charges are fixed in place. It's important to never draw positive charges moving. If the positive charges in this book were to start moving, then it would just fall apart into mush. The positive charges are part of the nucleus, and the nucleus is what gives an object its structure. Only the electrons in the book can move if it's going to maintain its structure and shape. And because everything we're told about involves charges moving, charges aren't destroyed, we can say that charge is always conserved. Just like we had the law of conservation of energy and the law of conservation of mass, now we have the law of conservation of charge. The law of conservation of charge says that charge cannot be created or destroyed, it can only be moved from one place to another. So if I take this dead rabbit, that's what it is. If I take the dead rabbit and rub it against the PVC rod, electrons will move from the rabbit to the rod, giving the rod a negative charge because of the extra electrons, and leaving the rabbit with a positive charge because of the electrons it's lost. It now has more protons than it has electrons. You can maybe even hear the static discharge. Then we can use this light piece of foil to detect that charge. If I move the rod that's now negatively charged close to the metal, it's attracted to the rod. But when we rub the two together, why do electrons transfer one way instead of the other? Why does the rod gain electrons instead of the rabbit fur gaining the electrons? That's electronegativity. Some materials naturally attract electrons more than others. If you have something high up the electronegativity scale and rub it against a material that's low on the electronegativity scale, electrons will transfer away from the electron donor and towards the electron acceptor. So that's how we can give things a net charge, an overall charge. But then why do they affect other uncharged objects? Why does the piece of foil move, for example? Or why does this balloon move? The reason for that again is how electrons are free to move. Metals have free electrons. They can move wherever they want inside the metal. So when I move a negative rod towards the foil, the electrons in the foil are repelled from the negative rod, since like charges repel, and they move to the opposite side, that leaves the near side of the foil positive, and since opposites attract, the positive side of the foil is attracted to the negative rod and they move together. But what about the balloon? A balloon is made out of latex. That's not a metal. But even then, electrons are still free to move within each atom. So what happens is when the electrons try to run away, they do so by spending more time on the far side of the atom than the close side of the atom. This produces like a layered sandwich of charges inside the balloon, with one side of each atom being slightly positive and one side of each atom being slightly negative. Each atom is said to be polarized, because it has a positive pole and a negative pole, almost like a north and south pole. The result of this is that the very edges of the balloon get a charge. The nearest edge of the balloon gets a positive charge and the farthest edge of the balloon gets a negative charge. And just like before, the near side of the balloon being positive is attracted to the rod, and so they move together. We instead got some repulsion, probably because some charges are transferred between the two objects, but polarization is still the main mechanism by which a non-metal attracts or repels. Another example, if I take that same balloon and I rub it against my hair, electrons rub from my hair onto the balloon, and then I can stick the balloon onto a wall. Kind of like that. Why? Here's an animation illustrating how it works. The electrons in the wall are repelled from the negative balloon and try to move away. They spend more time on the far side of their atoms, leaving the front of the wall positive. If the balloon is negative and the front of the wall is positive, those two opposite charges will attract, and so the balloon sticks to the wall. But rubbing two objects together, friction, is not the only way that you can give an object a charge. To demonstrate this, we're going to use a device called an electroscope. An electroscope is a charge detector. This is an electroscope. It's a charge detector. For the rest of this demo, I'm going to zoom in the camera so you can see the electroscope more clearly, and then I'll talk through what I'm doing as I do it. Okay, so the first thing I'm going to do is charge this rod using the rabbit hair. And then you'll notice that if I move it close to the electroscope, the two pieces of metal move apart from each other. And when I move it away, they move back. Next, I'm going to touch the rod to the electroscope. So they move apart, then I touch the rod to the electroscope and move away. And you'll notice that this time the metal does not go back to where it was. Then if I touch it with my hand, it returns. I'm going to do one more thing. I'm going to charge the rod up once more. I'm going to move it near to the electroscope but not touching. And then instead of touching it with the rod, I'm going to touch it with my hand. Now it appears to go back, but if I move away, when I move my hand away again, the electroscope does not go back to its resting position. These demos are examples of the two other ways that you can transfer charge. One is charging by conduction, by just touching an object instead of rubbing the object. When the PVC rod touches the electroscope, charges are transferred between them. The negative charges are transferred into the top of the electroscope. The charges actually leave the rod and move into the electroscope. They can conduct through the metal. Then when I move the rod away, they get stuck there. That leaves the electroscope with an overall negative charge. And since the metal as a whole now has a negative charge, the leaves of the electroscope repel each other. The third way is charging by induction. This one is the most complicated. When I move the rod near to but not touching the electroscope, the electrons run away down into the leaves of the electroscope. That's what makes them repel and move apart. But then if I touch it with my hand, since my hand is connected to the ground, is connected to the earth, the electrons see their chance to escape. They want to get as far away from the rod as possible. Since they can't go any further down the electroscope, the best way for them to escape is actually to run up the electroscope, through my hand, and down into the earth. By doing that, the electrons have left the electroscope, leaving it with a net positive charge. And since similar charges repel, the leaves move apart. One last thing, why did this happen? What did she do wrong? Pause the video and write down your ideas. Sometimes when static electricity builds up enough, it breaks through the air and creates a spark, like carpet sparks or even lightning. If the clouds can build up enough charge on their bottom layer by transferring that charge from the top layer, through friction between the different particles. That charge is enough to repel the electrons inside the ground away from the cloud, leaving the surface of the ground positive. If the cloud is negative and the surface of the ground below is positive, and that charge difference builds up enough, it creates a spark. The negative electrons are so attracted to the ground that they zap through the air to get to the ground. And when this lady got back in her car, she rubbed against the seat, building up static electricity on her, building up charge on her and her clothes. And then when she went back to the petrol pump and touched that nicely conducting metal, the charge saw its chance to escape and jumped into the metal, creating a spark. And with all the fumes rising, that spark created a fire. What could she have done differently? Well, not get in the car, for one thing. For another, all she had to do was release that charge in a safe way. If she had touched the metal of the car, because the metal connects to the ground through the tyres, the charge would have left her body, leaving her nice and neutral so that she couldn't have created a spark. So next time you decide to annoy your little brother, you'll not only know a good way to do it, but you'll be able to teach him some physics in the process. Ah, altruism. Thanks for watching Flip Physics. If you like this video, you can press the like button. You can also subscribe or go to the flipphysics.net website. But most of all, don't forget to leave a comment below with your questions, thoughts and suggestions. Until next time, keep questioning. I don't know about you, but these are my favourite kind of sparks.